Hello physics students, this is Mr. Downing. We're talking about Newton's second law. This is the law of acceleration. In the first law, we basically said that forces cause accelerations. This law answers how much acceleration. So our net force is directly proportional to mass and acceleration. So this is the equation F equals ma. Now, when we frequently see it like this, F equals ma, but this net is important on the force. It's the net force. We use this net a lot. Net means total. That means the total result of all forces. Okay, this is important because if I had an object here and it was being pushed to the right with 50 newtons of force, and someone was pushing it to the left with 50 newtons of force. So two different people pushing in two different directions, but just as strong, that's zero net force. Those two forces are completely canceling each other out. So it's not enough just to look at one, we actually have to look at the total forces, because that's going to affect what's happening. So whenever we have a net force, it causes an acceleration. Forces cause accelerations, not velocity. So if object A exerts a force on object B will accelerate because it has a force on it. Now, forces and acceleration are both vectors. They can be positive, they can be negative. So positive would be speed up, negative can slow down. Now, what some people get confused about is if I have an object and its velocity is this way, if its acceleration is this way, that means it's speeding up. Okay, so positive velocity, negative acceleration. If I have another object that also has the same positive velocity, I'm sorry, this was a positive acceleration. This is the negative. Negative means the other way. This would be slowing down. So a lot of students get confused that the acceleration has to be the same way it's going, and it doesn't, because acceleration doesn't mean which way it's going. That's velocity. So acceleration and velocity can be in two different directions. Now the acceleration and the force, the net force will always be the same direction, because that's what's causing it. Now this took a long time to formulate because it's hard to find the absence of friction. Here on Earth we'll always have friction because we're always moving around other stuff. If there wasn't friction, then no force would be needed to keep an object moving. It would stay in motion forever. So on Earth, force is needed to overcome friction to keep the object moving. So if a car in cruise control, the engine has to keep running only strong enough so that in my car, let's say its velocity is this way, the friction is pulling it down. Friction's slowing it down. The engine only has to be strong enough to apply the force to overcome friction. If the engine was stronger than friction, we'd actually be accelerating. But if we just need to keep moving, we only have to have enough to overcome the friction. Which means is forces are only needed to start an object moving or to stop an object moving. If we don't have friction, then we don't need force to keep it moving. So if you have a hockey player, and if he hits a hockey puck, and so after the puck has already been hit, it's just gliding across the ice. We use ice as a good example because it has very small friction. It still has some, but we just kind of pretend that little bit of friction, we just round it down to zero. So on ice, that hockey puck, it has a velocity this way. It's just coasting across the ice. It doesn't need a force. It only needed a force at the beginning, and there will be a force at the end whenever it hits the back of the goal or another hockey player's stick. But in the middle, when it's just drifting, no other forces are required to keep it in motion. It's not as if the hockey player has to skate behind it and constantly push. So now we say they are directly proportional. So if we have equal accelerations, so we're using the size of these letters to represent how big the numbers are. So this thing and this thing have the same acceleration, this elephant and whatever that is. They both have the same acceleration because they're both falling. So this elephant's falling and this bird or dead bird or whatever is falling. So the acceleration is the same. Now because the elephant has more mass, it means it has more force. because this dead bird has less mass, it has less force. So in this equation, F equals ma, because the F is directly across the equal sign from the m and directly across from the a, that means they are directly proportional. So what happens to one directly happens to the other. If I double my mass, I'll have double my force. If I have half the mass, half the force. So on and so forth. In this example, we consider what happens if, instead of keeping the same acceleration, what if we had the same mass in two different examples? So this car used in two different times. So the first time, we're just easing away from a stop sign, slowly increasing our speed. So we have the mass of the car, and then a very slow acceleration. It's going to take us a while to reach the speed limit. Very small force. If, on the other hand, we peel out, we have a high acceleration, and we reach that speed limit just in a couple seconds, we have a very high force. In this case, we can barely feel the car pushing us. There's barely any force. In this case, slam on the gas, and we are slammed to the back of our seats as that back seat of the car really pushes us forward. Directly proportional. Okay? That's Newton's second law. Just F equals ma.